Hi everyone, my name is Phumpon Botong. I'm from Cornell University. Today I would like to present a summary of our paper that is recently accepted at ICML 2024 conference. The title is Bayesian Optimization of Function Networks with Partial Evaluations. Let's begin by the motivation. Consider a manufacturing problem where we have the objective to identify an optimal amount of raw material that yields the highest quality of the final product we would like to make. This problem has two properties. First, it's expensive because each production we have to order an expensive raw material, and once we obtain it, we send it to the factory and wait a long time for the factory to produce the final product. So this problem is expensive both in terms of time and money. The second property is that the problem is black box because we could not write down a mathematical formula that describes how the amount of raw material correlates with the quality of the final product. Traditional approach that is suitable to solve this type of optimization problems is Bayesian optimization, or BO. BO begins by gathering initial dataset in terms of the input X and the output F of X. BO then trains machine learning model that is used to predict the output value at any unobserved input X. In the next step, BO used an acquisition function that evaluates the benefit that we could get from performing one more evaluation at any unobserved X. BO will suggest the value of X that maximize the acquisition function value because this value is the most promising one that we could get the most information about the function being optimized. We then follow the recommendation by evaluating the true objective function at the suggested X. Now we have one more observations. We update the dataset and repeat the process again until we find the optimal solution. Traditional BO treats problem as black box because it will use only the input and the output to fit a machine learning model that is used in the framework. Bayesian optimization of function networks, trying to open the box to see is there any additional information that we could use to improve the sampling efficiency, with the goal that trying to identify a better solution with spending smaller amount of evaluation budget. For example, in the production process, it actually consists of several steps. Like the raw material has to go through the heating process first, and then we will observe the intermediate outcomes from the first process. These intermediate outcomes will be fed into the second process to produce the final product. Standard Bayesian optimization would ignore the intermediate information, the intermediate outcome, and would use only the input and the final output to fit a machine learning model to use in the framework. BOFN, on the other hand, trying to come up with a better, a more accurate machine learning model to use in the framework. So basically, it will try to fit an individual model for each individual step. Like the step F1, it will use the input X and the output Y1 to fit an individual model for the step F1. Similarly, the step F2 will use the output Y1 from the previous node as the input and its own output Y2 to fit an individual model for F2. BOFN will use this composition of a machine learning models in the framework. Doing this result in an improved sampling decisions. We could locate a better solution with spending smaller amount of evaluation budget. However, the current BOFN algorithms has the limitation that it requires full evaluation. Once we make a suggestion on the value of X, we have to compute until we obtain the final value. Imagine the scenario that we have worked on a value X of the material through the first process, and the result turned out to be not that good. What should we do if we know that the second process is much more expensive? Should we either stop or continue? The contribution of this work, we would like to propose a novel BOFN framework that allow partial evaluation for a general network. So basically, we need a framework that make a decision to evaluate only a part of network that is the most promising. In order to do that, we introduce a knowledge gradient acquisition function that we call PKGFN, where P stands for partial evaluation, that evaluates the benefits of additionally evaluating just a node in the network, like how much benefit we would get towards the goal of maximizing the final node value. This acquisition function will choose a node and its input to evaluate at each iteration. Finally, we compare the performance of the proposed PKGFN algorithm to the existing BOFN frameworks. We found that allowing an algorithm to do the partial evaluation, just evaluate a part of network at a time, could improve the optimization performance by a lot. We could locate a better solution. We are maximizing the function. We could locate a better solution, a higher value of the objective function with spending much smaller evaluation budget. If you are interested in this work, you are welcome to see us at our poster. We will give a presentation in poster session 3 at hall C429, the poster number 1205. And the presentation will be on Wednesday, July 24th, starting from 11:30 to 1 p.m. Thank you.